Buffers are solutions that can resist drastic changes in pH. Now, you might ask, what does drastic mean? Or how can we say that a change in pH is already drastic? I usually consider a change in pH value by 1 unit as drastic. So, for example, if you have a solution that has a starting pH value of, let's say, 6.5, and if I added an acid and the pH dropped to 3, then that is drastic because the pH value changed by more than 1 unit. But for example, if the pH of the solution starting from 6.5 only dropped to 6.1 when I added the same amount of strong acid, then it's a buffer. It's a buffered solution because the change is only zero point 0.4. Now, to understand further about this capacity of the buffer to resist drastic changes in pH, we need to understand one equation. We call this the Henderson-Hasselbalch equation. This is actually a very important equation when we talk about buffers. In fact, it is the only equation that you need to know and understand when you are making computations regarding buffers. So this is your Henderson-Hasselbalch equation. So pH equals pKa plus logarithm of the concentration of conjugate base over the concentration of the weak acid in your buffer. So we see the concentrations for the two components of your buffer. And then we need the Ka value. Do you remember your acid dissociation constant, or the Ka? So we need the Ka value of the weak acid component. And using this equation, you can actually compute for the pH of your buffer. But this equation, as we will see later on, is very versatile, and this is the equation used when you want to prepare a buffer. And we will go on that later. But now let me show you where this equation came from. If you recall, let's say I have, again, let's use acetic acid as an example. So this will be the weak acid component of our buffer. And I will write first its dissociation reaction in water. So I have acetic acid plus water. And now I'm writing a double-headed arrow because it's a weak acid. Then we have the conjugate base acetate plus hydronium ion. We write the equilibrium constant expression for this dissociation reaction as the concentration of our products. So we have the concentration of acetate times the concentration of hydronium ion over the concentration of acetic acid. So recall, we don't include pure liquids and pure solids in our equilibrium constant expression. That is why we don't see water here. Now, what we will do is we will get the negative logarithm of the two sides of the equation. So I have negative log Ka equals negative logarithm of this whole expression over concentration of acetic acid. Now, negative log Ka is your pKa. So remember, anything that you get the negative logarithm, that's P of that thing. Okay? So you recall the formula for pH. The formula for pH is negative logarithm of the concentration of your H plus. So for example, if I want to get P Na or P sodium, that means I just get the negative logarithm of the concentration of sodium ions in my solution. So negative logarithm of Ka is pKa. So we have pKa on the left side of our equation. Now, I want to separate the concentration of hydronium ion. So I have negative logarithm. Since this is a product, so I have negative logarithm of the concentration of hydronium ion plus negative logarithm of the remaining part of our term or our expression. So that's negative logarithm concentration of acetate over concentration of acetic acid. Now, what is negative logarithm concentration of hydronium ion? This is also pH, right? So H3O plus is just H plus with a water attached to it. And basically, these two are the same. So we now have pKa equals pH. So this one became pH. And then we have plus minus. So we have minus logarithm of this ratio over acetic acid. Now, let's just rearrange this equation. So we transpose this term, this logarithmic term to the other side, and we have pH remaining on one side of the equation. So we have pH equals pKa plus logarithm of the ratio. And if we generalize this equation, we have the Henderson-Hasselbalch equation. So notice in our ratio, we find the conjugate base in the numerator and the weak acid in the denominator. So this is your Henderson-Hasselbalch equation. Later on, you will see how this equation is used in the context of buffers.